Good afternoon. Today we will discuss the conservation theorem of energy of system of particles. Conservation theorem of energy for system of particles, that is state and prove the conservation theorem of energy of system of particles. If the total energy of system of particles in initial position 1 is equal to the total energy of system of particles in final position 2, or if the conservative force acting on a system of particle, then its total energy remains constant. Total energy means that is the sum of kinetic energy and potential energy remains constant or constant. For this purpose, consider the system of particles, and system of particles contains there is the n particles, and out of these n particles consider only one, that is the ith particle. Ith particle. This ith particle having the mass is the mi and velocity is the vi. Mass is the mi and velocity is the vi. Then the kinetic energy of ith particle, kinetic energy of ith particle is equal to Ti equal to 1/2 mi Pi square. That is the kinetic energy, nothing but the half mass into square of velocity. Let Fi be the force acting on a Fi be the force acting on a ith particle. Due to this force, the ith particle, this is the ith particle, displaced from initial position, first position, to second position, through a small distance, that is the dr. Then work is done. And work done between the initial position to final position is given by of ith particle. That is the W, work done from initial to final position of ith particle is equal to integration from position first to position second, that is the force into their displacement. Which is equal to integration 1 to 2. Force is the Fi acting on ith particle into displacement is the dr. But force Fi acting on ith particle is nothing but the rate of change of momentum with respect to time, that is the dpi by dt, which is the momentum, that is the linear momentum, that is the pi is nothing but the product of mass and its velocity, that is d by dt of product mass mi into pi, which is equal to mi into dpi by dt. And dri is equal to pi into dt. In this equation, we get work done from initial to final position of ith particle is equal to integration 1 to 2 w1 to 2 of ith particle equal to integration 1 to 2 Fi means that is the mi into dpi by dt into dri means that is the pi into dt. This dt gets cancelled, which is equal to integration 1 to 2 mi into pi into dpi. Mi is the taken outside the integration into integration 1 to 2 pi into dpi. Now that is the integration by using the standard result of integration. Integration of x raised to n into dx equal to x raised to n plus 1 divided by n plus 1. Using this relation, we get W work done from initial to final position of ith particle equal to mi into integration of phi, that is the phi square divided by 2 between initial to final position. Now put upper limit minus lower limit, we get 1 by 2 into bracket mi into vi square between initial to final position. But here that is the 1 half mi into vi square is nothing but the TR, that is the kinetic energy between the initial to final position. Now taking the summation on both sides, we get work done between initial to final position, which is equal to summation work done initial to final position of ith particle equal to summation of TI between 1 to 2, which is equal to T between the limits 1 to 2, which is equal to T2 minus T1. Put upper limit minus W1 to 2 equal to T2 minus T1. This is the equation number first. That is the work done W1 to 2 equal to T2 minus T1 is the equation number first. Now potential function, that is V, that is the minus del grad means that is the del V R, that is the Fi equal to in this, that is which is equal to negative gradient of dVr by dRi. Putting these values in the equation, work done 1 to 2 between the of ith particle between initial to final position equal to integration 1 to 2 Fi means that is the minus dVi by dRi into dRi. This dRi gets cancelled, and here integration and derivative are opposite to each other and cancel, which is equal to minus Vr between the limits initial to final position of 1 to 2. Now put or taking the summation before putting the values upper limit minus lower limit, that is the taking the summation W1 to 2 of ith particle, we get work done between initial to final position equal to summation of work done 1 to 2 of ith particle, which is equal to summation into bracket minus of Vr between the initial to final, which is equal to minus into bracket summation of Vr 1 to 2, and summation of Vr is nothing but the potential energy of system of particles, that is the minus into bracket V between initial to final position. Now put upper limit minus lower limit, we get W1 to 2 equal to minus into bracket V2 minus V1, which is equal to V1 minus V2. This is the minus and minus minus plus, that is the V1 minus V2. This is the equation number second. But from the equation W1 to 2 equal to T2 minus T1, W1 to 2 equal to T2 minus T1, and W1 to 2 equal to V1 minus T2, we get T2 minus T1 is equal to V1 minus T2. That is T2 plus V2 equal to T1 plus V1. T1 plus V1. That is the kinetic energy at the final position is equal to kinetic energy. Sorry, not kinetic energy. Sorry, T2. This is the kinetic energy at the second position plus V2 means that is the potential energy at second position, which is equal to kinetic energy at initial position plus potential energy at initial position 1. That is kinetic energy plus potential energy is nothing but the total energy, that is the TE at the second is equal to TE at the first. And from this equation it is clear that the total energy of system of particle at the initial position must be equal to the total energy of system of particle at the final position. Okay.